All right, thank you very much. Does this show up? All right, it is a great honor to be here at Warsaw, my first time at Warsaw. There's, I think, a deeper connection because I should say that the the patron of Monash University, John Monash, actually had roots hailing from Poland. So it's very nice to sort of revive this connection for the first time, even though it's a very old and very indirect one. All right, so good. I've been given the task of lecturing or presenting, I think it's going to be something in between, on core collapse, supernova theory and modeling and gravitational waves from the simulations. Now that, I must admit, also given that we have a very diverse audience, supernova modelers, gravitational wave people, is probably next to an impossible task. The task that I was given was by the organizers, Marek and Tony, was exactly this, which to me seems extremely daunting to go both into the fundamentals, into the state of the art and what's missing. I'm not sure I can do justice to that within 90 minutes. So I do want to remind people there's a lot of good work out there, some of it written by other people here in the audience, on precisely those topics that I'm supposed to cover. And as the focus of my task was to actually also go back to the fundamentals, I will actually go back to some fundamentals and try to walk everyone through what a core collapse supernova works like, what it looks like. And during the first part of this double talk, I will probably focus much less on the results and much more on the basics, even though there are some things in there that I think we have learned about the basics and that have clarified our picture in the last decade or so. All right, so to remind everyone about the basic picture, we start core collapse supernovae from massive stars. Massive stars evolved through several burning stages to this famous onion shell structure. They may or may not have retained their hydrogen envelope. And once you're through core silicon burning and then the phase of shell silicon burning, your iron core at the center becomes big enough and still grows to a point where the degeneracy pressure can no longer support it, and it will collapse on a free fall timescale to a neutron star initially. We call that proto-neutron star. And as we'll revise in the next few slides, an explosion doesn't immediately follow. The explosion has to be triggered by some form of delivery of energy from the neutron star to the surrounding material that eventually makes the shock wave that was formed when the neutron star first formed to a point that it can move out dynamically. And I think on the highest level, you're all familiar with maybe the two basic scenarios, and then maybe this third one that one person here in the audience has championed very much, Tobias Fischer, which may also apply under certain conditions. So you either pump energy into the ejected material by neutrinos that come from the proto-neutron star and heat its surroundings.
Can you share the screen?
On Zoom?
Zoom, yeah.
Okay, what's the Zoom link? Not a problem.
(304)
304
1505
1505
254
254.
Yeah, you can mute yourself.
Recording in progress.
Muted, okay. And so everyone can share on Zoom as well. All right, good. All right, so the basic scenarios, you either deliver energy from the neutron star via neutrinos. We'll look into that in more detail. That's what we think powers the vast majority of explosions. For the outliers at the very high energy end, we think that some mechanism that involves the delivery of or the tapping of rotational energy by magnetic fields is involved, either from a neutron star or from maybe a black hole accretion disk. And then there's this other scenario that we may also talk about at this meeting that has been brought up by Tobias Fischer, which is that you could have a second collapse at some point where a phase transition triggers a collapse and then a second rebound and then a shock forms. The parameter space for that, I think, is probably narrow and is not going to explain. It's maybe applied to a subset of cold collapse supernova explosions, but I think these three are the ones that deserve to be mentioned. Now let's first go through the entire story from collapse to explosion, focusing mostly on the neutrino-driven scenario. I will say a very few things about magnetic fields, though. And even though this may be very basic to some of the modelers, I think I still wanted to bring that up because what this first part also intends to do is, of course, tends to draw up the backstory for the various phases of the gravitational wave emission that I'm going to discuss in the second part of this talk, right? So we start our collapse from an iron core. Degeneracy pressure is no longer sufficient to sustain the core. You get collapse on a dynamical time scale at densities of order of 5 times 10 to the 11. The neutrinos that you make from electron captures can no longer get out. They're trapped, so the electron fraction is frozen at about that point, but the collapse continues until you reach densities in excess of nuclear density, and then the repulsive nuclear forces lead to stiffening of the equation of state. You get a rebound of this core, which is now a young protoneutron star, and you form a shock wave. Yeah, and the shock wave is quickly drained of energy, quickly stalls, because you lose about 10 to the 51 ergs per tenth of the solar mass just to dissociate the material that the shock is moving through, and that immediately, within milliseconds, drains the initial kinetic energy of the rebound in the shock wave. Right? Now, this bounce phase, this collapse, bounce, and rebound phase is well understood. We also know that there is some sensitivity to the microphysics. There was seminal work that was done now more than 20 years ago, again by several people in the audience, that clarified really how big this inner core is at bounce. And that is not, so that's now something that we all take for granted. But this fact that the microphysics actually does influence the collapse and rebound dynamics a bit is something that one should bear in mind when you're talking about certain components of the gravitational wave signal. I'll come to that, because the initial energy of the rebound will translate into things like what's the initial entropy profile that you generate as the shock moves through the inner material, and that will affect things like what kind of instabilities develop shortly after the bounce phase, like this phase that happens when the shock hits optically thin material, and the entropy gradient behind the shock starts to become negative. That's this phase that we know as prompt convective overturn. That is something that is actually slightly, or not insubstantially, sensitive to some of the microphysics that you're using during this phase. So the transport treatment that you're using during this phase, the initial entropy profile that you set during the collapse bounce phase. That is something that's a signal component that will generate a signal component of the gravitational waves that some people have actually asked me about before the meeting. So I'm bringing up the fact that even though this early physics of core collapse is well studied, has been for decades, and seems well under control, when we're talking about the details, which may matter for the gravitational wave signals that you get from this phase, where the negative entropy gradient that develops behind the shock for a short time, their details of the microphysics may actually matter to what the gravitational wave people need. right? So, but that's for the supernova modelers, that's probably rather boring stuff. What matters for us is that, well, you get this phase of the prompt convective overturn that mixes this material behind the shock, and it very soon, within milliseconds, tens of milliseconds, becomes stable, and you eventually develop something of a quasi-stationary situation. The shock will still travel outwards quasi-statically. It has turned into an accretion shock, so matter behind it is no longer moving outwards, but it's still, just by the jump conditions at the shock, adjusts its position, and it moves outwards within tens of milliseconds to about 100 to 200 kilometers, hovers there for a while, and then after 100 milliseconds or so, you will actually see the really interesting thing for the neutrino-driven mechanism, which is that a structure with a neutrino heating will develop, net neutrino heating, and I will come to that in the next slides. You will see also that the infall of material from the outer shells is going to change a while. So what's shown here is actually slices from a very old paper through the entropy of a simulation. And you see here, the entropy here changes at some point. That's a shell interface from the progenitor. And that actually has implications for the dynamics of the shock. The shock will react to that because you will have less accretion rate and less of a ram pressure acting in front of it. And eventually, at some time, which may be close to the time when that shell interface reaches the shock may actually start to move outwards because it's heated, because the post-shock material is heated sufficiently by neutrinos. All that may happen later. That's just a very schematic picture of how the first few hundreds of milliseconds in a core collapse supernova look. Right? So shock traveling to about 100 to 200 kilometers, then you might have some wiggling of the shock, feeling less secretion, ram pressure when the shell interface between the silicon and oxygen shell comes in. You might have more of a phase where the shock is still stalled, and eventually you get into an explosion. Yeah. So this is just really for everyone, including the non-modelers, to sort of get an overview of the phases that we are seeing in core collapse supernova explosions, the phases that we're going through in the phase where we get probably the most interesting gravitational wave emission. Some gravitational wave emission may actually still come later, but that's subject of the very late part of this talk. All right, so one of the things that also was implicit in the task set to me by the organizers was to sort of develop or set for the further discussion and the talks set up something like a common vocabulary, common terminology. And for that, I think it's just nice to have a look at the radial structure of this supernova core in this phase from about 100 milliseconds after the neutron star, after the protoneutron star has formed. And you have this more or less quasi-stationary accretion shock, which is, at this radius that I mentioned. And then the structure that develops if you start from the inside. So at the very inside, you have a really supernuclear core of supernuclear density, right? That is actually, in terms of thermodynamics, in terms of entropy, it's cold core, low entropy. Then that's surrounded by what I usually prefer to call a mantle, which has moderately high entropy. That's been shock heated shortly after bounce. That may still have, so much of that will be at subnuclear, but close to nuclear densities. And then there's a cooling layer at the top. So that's where the neutrinos densities are low enough for the neutrinos that come from the accreted material or from deeper inside the neutron star to stream out. So in that conditions where you have an optically transparent or semi-transparent region where neutrinos can efficiently redistribute energy, that will give rise to an almost isothermal atmosphere. So such an atmosphere has a structure which is governed more or less by an exponential decay with a density gradient that's related to the temperature. So the cooler the temperature, the steeper this decay, and the stronger the gravitational acceleration, the steeper this density decline. And then at yet lower densities, because of the ways the neutrino emission and absorption rates work out, that transitions into a region where you have net neutrino heating. And that region, so in that region, you have matter that's been falling through the shock, moving towards the neutron star. It's heated by neutrinos, but the heating by neutrinos during this quasi-stationary phase is still relatively weak. So that material remains almost, not perfectly, isentropic. And the result of that is a relatively flat, is a power law stratification that goes with about r to the -3 in density, right? So bear these regions in mind, the regions where we have the neutron star core, really high density, slightly higher entropy, the mantle, then the cooling region where there's a steep density gradient, then the heating region. We will see later on, relevant to gravitational waves, that two of these regions are subject to hydrodynamic instabilities, namely this mantle region and this heating region, whereas this interface between the mantle and the core is stable against hydrodynamic instabilities, and the cooling region also tends to be stable against hydrodynamic instabilities, at least in the non-convecting, in the non-rotational case. All right, so the neutrino heating emerges simply because of the effective radial dependence of the heating and cooling terms. If you have neutrinos streaming off from the neutron star surface, the energy density of the neutrino radiation field will go roughly with 1/r², modulo the flux factor, so the ratio of the neutrino flux and energy density. And that results in a heating rate that goes with r to the -2, whereas the cooling of neutrinos tends to be, if it's proceeding primarily by electron or positron captures, that tends to be under these thermodynamic conditions, relatively hot non-degenerate matter, that tends to be proportional to T to the 6, and that gives rise to a radial dependence of about r to the -6, which implies that eventually, once the shock has traveled far enough outward during this quasi-stationary evolution, there will be a region where the neutrino heating wins and where you get net neutrino heating. Okay, now the question is then, when do you get into explosion by neutrino-driven explosions? And the answer is, of course, in the simplest possible terms, that the neutrino heating has to be sufficiently strong. What does sufficiently strong mean? So Thomas here has worked on coining the relevant concepts almost 25 years ago, and they still hold and were, I think, confirmed in the last decade or more than a decade by various people who have done conceptual simulations or also the real full-scale physics simulation. The essential thing that dictates whether or not you explode is, well, you have the matter falling through the shock accreting onto the neutron star. That has a finite binding energy. It's bound. If it's heated by neutrinos, and if the neutrino heating can pump enough energy into that material to make it unbound before it falls onto the neutron star, before it settles onto the neutron star, then you will get a non-stationary situation. Then this thing here will no longer be stable, and you will get into a runaway situation, because if the post-shock region adjusts, that, well, you have enough energy for the accreted material to build up some extra pressure that will feed back onto the shock. The shock will expand. If the shock expands, you have more time to heat the material. So the situation becomes even more extreme, and you can pump in even more energy into the material, and this way you get a runaway. Yeah, the way Thomas phrased this many years ago was by considering these two timescales. So what's the timescale for unbinding material by neutrino heating? That's the heating timescale. And what's the time that the material spends in the heating region? So the time that is available for it to be heated, that's the advection timescale. And if the advection timescale is longer than the heating timescale, you can get into a runaway situation. And that eventually is something that can be translated into conditions for the neutrino luminosity to be sufficiently high in order for that timescale ratio to be favorable. So it's been worked out that effectively this translates into a condition for the neutrino luminosity to be above some critical threshold, critical neutrino luminosity, such that this ratio here is bigger than 1. And with all these equations that I mentioned, I should, of course, flag that everything that we're talking about here is a simplification of the simplified reality that we see in simulations, but the equations are nonetheless something that is important for us to sort of order our thinking about the core collapse supernova problem. They're just shorthand for communicating. Bear in mind that none of the equations that I'm showing here for such a complex problem really does all of justice to reality, but they're nonetheless useful. All right. Now, what dictates whether or not you go into explosion? So there's been a lot of phenomenological study of that topic for the last decade in 1D, 2D, 3D simulations. And one thing that we certainly recognize, and I think that is now very firm, is that the progenitor structure of the star matters very much. The progenitor structure is effectively what dictates what the accretion rate and hence also the ram pressure on the shock is. That needs to be overcome by neutrino heating that generates enough pressure behind the shock to exceed that ram pressure. If the post-shock pressure exceeds the pre-shock pressure, then there needs to be adjustment to fulfill the jump conditions and the shock moves out, right? And the density structure of the progenitor stars effectively translates quite directly into the history of the mass accretion rate. One or certain points in the stars are always very important in that respect, because the stars prior to collapse, they have structures, a core, iron core, silicon shell, oxygen shell, and so on. And those all have different entropy. That translates, if you solve the hydrostatic structure equations, that translates into jumps in the density at these shell interfaces. And because the density profile is directly related to the accretion rate after collapse, that translates into the time-varying accretion rate. So the density structure of the progenitors, and in particular the properties of the oxygen-silicon shell interface, has been recognized as very important for dictating whether or not an explosion occurs. It's often the natural point where an explosion kicks in, because at that point the ram pressure is going down. And also some of the criteria that have been formulated based on phenomenological models, as well as more complex multidimensional models, or at least gauged within those complex models, like the compactness parameter by O'Connor and Ott, or the Garching criterion, the Ertl criterion with these parameters for the size of the silicon oxygen core, effectively, and for the density outside of this silicon oxygen shell interface. They effectively reflect that these shell interfaces really play a critical role. They're the ones that determine critically influence the shock position by giving us a point where the accretion rate and hence the ram pressure on the shock can drop relatively abruptly, yeah, and then trigger dynamics, altered dynamics in the balance between the stabilization of the shock by ram pressure and the heating behind the shock wave. Right. Now, it's been recognized for a long time that neutrino heating, although it is what we would call what I would call the mechanism that pumps the energy into the explosion. So ultimately, the thing that really makes the material unbound. The neutrino heating alone is not sufficient to account for the explosions that we see in nature. And for a long time, actually going back even to the 90s, it has been recognized that hydrodynamic instabilities in the supernova core play an important dynamical role. Now there are, if you count all of them, there are lots of hydrodynamical instabilities that can occur in the supernova core. And of course, the hydrodynamical instabilities are also the one thing that is most interesting to us if we're coming from the perspective of the gravitational wave astronomer, because the hydrodynamical instabilities, the non-spherical flow is what we see in gravitational waves, right? Spherical dynamics is boring for gravitational wave astronomers. Right, so the important hydrodynamic instabilities, or the most important ones, because you have neutrinos heating an accretion flow. The neutrinos will create an unstable entropy gradient. They will create a slightly negative entropy gradient. The material that has moved further to the neutron star has been heated more. That means it has higher entropy, has accumulated entropy, and that makes this region, the heating region, unstable to convective overturn. There's another instability that has been discovered by Tony many years ago. This is called the standing accretion shock instability. So there's also in this accretion, stationary accretion context, there's a genuine instability of the shock that has nothing to do with convective instability and heating. And I'll get into that also on one of the next slides. Finally, there's another region in this neutron star mantle that is unstable to convection. In that respect, it's the other way around than in the gain region. Here, it's the fact that you're losing heat and you're losing lepton number from the neutron star surface that makes this mantle region unstable to convection. And of course, on top of all of that, you could also have rotation. And the rotation can trigger various types of instabilities. The rotation can trigger instabilities that result in the growth of magnetic fields. It can result in genuinely hydrodynamic instabilities like triaxial instabilities, below T over W instability, for example. So there's, in principle, lots of instabilities that can give rise to aspherical flow that you can then see in gravitational waves. And there are, as I already said previously, there are stable regions sandwiched in between as well. So this neutron star surface region where you're dominated by cooling, that's stabilized against convection. And that's also interesting because in such stable regions, you can maintain oscillation modes of definite frequencies. And those are also interesting because, well, if you just measure a spectrum of something in some form of gravitational waves, it's much harder to pin that, to connect that to a single physical quantity, a single number that this measures. So the fact that we have these stable regions that can maintain oscillation modes of definite frequencies is also interesting. There's another stable region inside as well, inside this mantle region that's also stable, and you can also have oscillation modes living there. I'm simplifying things a little bit because, of course, in these convectively stable regions, you can actually still sustain some form of oscillation modes as well. So oscillation modes with pressure as the restoring force, those can also live in these convectively stable regions. All right. Now, let's go through some of these instabilities. I've already explained more or less what the convection is about. So you have an accretion flow which is heated, and because of that, you establish the unstable entropy gradient, negative entropy gradient, that leads to overturn. The fact that this is happening in accretion flow has some implications because, as we've learned, no question. Because as we've learned, that's work by Thierry Folizzo, the condition of a negative entropy gradient is actually not sufficient for the flow to become unstable. The flow has to be sufficiently slow, as it were, for the convective instability to kick in faster than the advection timescale, effectively. So you can form a criterion for that. The characteristic frequency for convective overturn or convective instability, the Brunt-Väisälä frequency, has to be longer than a certain fraction, then bigger than a certain fraction of the inverse of the advection timescale. One of the very important things that we've recognized in the last decade is that the convection in this heating region is not purely chaotic. So it actually reaches a steady state where the energetics of this convection are really very nicely determined by the parameters of this shock region and the neutrino heating. So effectively, you get a cubic root of the product of the heating rate times the extent of the gain region that dictates the magnitude of the velocity fluctuations. The reason why I'm mentioning this here in the context of this conference is that this, of course, if you know what governs the energetics of the convective flow, this is something then that you may potentially look for in your gravitational wave signals. This is one of the parameters in the, well, maybe not so near future, but for next generation instruments that you're interested in measuring, right? You're interested in measuring anything that may relate to something like the energy contained in certain convective motions and certain instabilities. Yeah, when you get your emerging gravitational wave spectrum and total power and so on. That's a long way off, but this is what I simply also want people to think about, right? So at some point, when we're really lucky and we get a galactic supernova, we don't just want to say, we found it, but we want to think about what can we actually measure. Now, the standing accretion shock instability, as I said, been discovered by Tony, and then people like, I think Jérôme Guillet is also here. He's not coming, okay, but he was telling me he was interested in this conference. So Tony and the Paris group have worked very much on this instability. So what happens there is when you have the standing accretion shock, you can have a situation where you have waves traveling between the shock and the neutron star surface, and then at the neutron star surface, you can couple your wave in what we probably believe, or Thierry and Jérôme have worked out, vortical waves from the shock will then get converted into acoustic feedback from the neutron star surface, and then the acoustic wave travels out, they then perturb the shock, and if conditions are right, you can get a positive feedback cycle, and you can get an instability. Yeah. The interesting thing is, as I said before, this has nothing to do with the fact that you're heating the material. In fact, if you heat the post-shock region too much, then you will tend to probably disrupt this cycle by the convection. So you effectively get a regime where you can get an instability that can develop under conditions that are not favorable to convection. One interesting thing about the standing accretion shock instability is it's an instability that has a definite spectrum, so it grows with a very definite periodicity, yeah, which is again something that you can then potentially look for into gravitational waves and think what this might tell you about the supernova core environment. Like convection, the standing accretion shock instability will have some saturation behavior, so the energetics is something that I think we also worked out more or less. So qualitatively, what happens is that saturation of this instability appears to be determined by parasitic instability, so you get sloshing motions and spiral motions of the shock. You get a complex structure of an oscillating flow, and on top of that, you develop instabilities like Kelvin-Helmholtz instability, which sort of take energy out of the large-scale motions that characterize this sloshing and spiraling standing accretion shock instability. Yeah. Now, what we've also learned in the past decade or so was really how these instabilities interact with the explosion conditions. Yeah, that what they effectively do by various effects. So this cannot be boiled down, I think, to a single physical effect or a single terms in a turbulence theory of the flow. What they effectively do is they add various things like turbulent pressure, they add turbulent viscosity, they transport heat around, and effectively that results in conditions that allow the shock to expand further than it would under completely spherically symmetric conditions. That, of course, means that then, of course, your time available for neutrino heating in the accreted material goes up, and your timescale ratio between advection timescale and heating timescale becomes favorable. If you turn that around to what that means for the luminosity that you require to heat the material sufficiently for explosion, that means that this will go down. And the relevant order parameter, as it were, is really the turbulent Mach number of this aspherical flow behind the supernova shock. So the ratio of the magnitude of the velocity fluctuations, the aspherical velocity components, to the sound speed. If that's sufficiently enough, then that will help you get into a runaway driven by neutrino heating more easily. A minor complication, or at least, well, it's not a complication. Technically it's a complication, but it's a benefit for the supernova modelers and for the explosion mechanism that has been also recognized in the past decade, is that when we talk about these hydrodynamical instabilities, it matters that the stars prior to collapse are already aspherical. Yeah, why are they aspherical? Well, because you typically have active burning regions around the core. Almost always active oxygen burning, sometimes active silicon burning, and those burnings tend to drive convective shells, right? So you already have convective turnover motions in the star before it collapses. So that means when the stuff falls through the shock and onto the neutron star, you already have seed perturbations to trigger and boost your hydrodynamic instabilities, and you also start to modify the flow globally. So what happens effectively is that even though your convective velocities prior to collapse may not be very fast, they still translate very effectively into ram pressure perturbations ahead of the shock, and then can sort of guide the shock and tell, well, here's less ram pressure. This is where you can expand more easily. And that actually turns out to be in, I think, all the simulations that or many of the simulations that have been done using multidimensional progenitor structure, which is unfortunately not nearly as commonplace as we would like it to be, is another beneficial effect that effectively lowers the amount of neutrino heating that we need for explosion by an amount that's effectively dictated by the Mach number and also dictated by the scale of these convective motions in the progenitor. The larger the scales, the bigger the effect. Finally, so the other hydrodynamic instability that I mentioned is the one in the protoneutron star, the convection in the protoneutron star driven by heat and lepton losses. The protoneutron star convective region is certainly an important driver that we need to consider for the gravitational wave emission. Its effect on the heating conditions, on the dynamics, is a little more subtle. What it does is it modifies the neutrino emission a bit. It modifies effectively the boundary conditions of the region behind the below the heating region a bit by affecting the neutron star radius. And its dynamics is actually, if you look at it closely, which I can't do now, is actually amazingly complicated, because you have a lot of interplay between different stabilizing and destabilizing gradients of lepton number and entropy number, lepton number and entropy. The dynamics of this region is a very subtle hydrodynamic phenomenon. It also has potential repercussions on the neutrino emission. So there seems to be a low mode instability called laser, which we discovered again, more than a decade ago, which can give rise to an asymmetric distribution, hemispheric distribution of lepton number that then translates into asymmetric emission of lepton number away from the neutron star. I can only bring that up here and say for much of the explosion dynamics, it's not a factor that we usually consider very much, but I nevertheless wanted to bring up that we have this unstable region because it matters for gravitational waves. Finally, I will say something about magnetic fields. So the magnetic fields are in the progenitors probably of an order that direct amplification by flux compression, which goes with, does not actually make them usually big enough to matter dynamically. So various instabilities would have to drive amplification to dynamically relevant field strength. This can happen both in the non-rotating context as well as in the rotating context. So in the non-rotating context, you can simply have a small-scale dynamo. In the context of rotation, you can have the magnetorotational instability, and as a fast instability, as well as other kinds of dynamos that will be especially important for the later phases of proto-neutron star evolution. And you expect, just dimensionally, I think, for all of these rotationally driven instabilities, that you will get saturation that is where the field strength are more or less determined by the shear, the amount of differential rotation in the proto-neutron star or its environment. Now, in the last 5 minutes, I don't have very much to say about the current state of simulations, but I shall still say a little about the complexity of this problem. The complexity of the problem that we are facing in actually simulating core collapse supernova explosions. You have to put all of what I said together, hydrodynamics, magnetic fields, and also everything that I haven't talked about, like the neutrino transport and the myriad of complexities in the neutrino transport that we've barely begun to scratch, like the issue of flavor conversion due to fast flavor conversion, where some people have started to sort of approach the problem and combine what we know from neutrino physics with actual simulations. The entire problem, neutrino physics, hydrodynamics, magnetic fields, general relativity, multidimensional progenitor structure is so complex that we really don't have any model that can perfectly combine all of this. And that creates a challenge. How do you deal with such a multi-physics problem? How do we make further progress? And we have identified really many factors by looking at the various aspects of this multi-physics problems that are instrumental in allowing to account for explosions, but that nevertheless that also means we're looking a bit selectively, right? So we may not have overlooked factors that compensate beneficial effects that we're seeing. That also means that, well, none of us really have everything in our simulations to account for the perfect model, right? So any tensions that we still see with observations, they might simply be due to the fact that we're not covering this multi-physics problem as comprehensively as we would perhaps like to. But nevertheless, a bit of an overview of where the status of the field is, and this is probably very subjective, and I'll also tone it down to some degree because I don't want to just give my take, I want to stimulate discussion. I think we're at a state now where many different groups have come up with successful explosion models with complementary, somewhat different methodologies. Some of us get lots of explosions, some of us maybe get too many explosions across the progenitor mass range. And there are some, and that's also important, that we may not see because it's not published, that maybe don't get explosions across the entire progenitor range. So I think we're at a stage where the fair thing to say is we're able to account in principle for neutrino-driven explosions, but I would be very let's say, careful in saying any definite things that we already know. I think even when it comes to questions like which stars explode, we are still facing some discrepancies between the results of different groups that need to be resolved. We may also still face some, or even the successes that we have, or some groups have, in being able to account for a lot of explosion models, including explosions associated with black hole formation. We now need to ask ourselves, do we have tensions with observations? Do the models explode in the mass range where they should explode, and do they fail in the mass range where they should perhaps fail? We should, of course, also note that even observational constraints on ranges of explodability from progenitor masses are something that is, in recent years, I think, becoming a little more, seeming a little less certain than it maybe was a few years ago. About explosion properties, and I'll move close towards the end, I think despite the uncertainties that we even have about mass ranges of explodability, I think there's also maybe something of an emerging consensus that what we see is trends towards bigger stars with bigger cores exploding with higher energies if they do, also exploding, making bigger neutron star kicks if they explode. Yeah, and what we're also seeing is that when we get explosions, the energy ranges of observed typical explosions are within reach. So it's no longer a mystery that we can get explosions of 10 to the 51 ergs. And also the ranges of kicks that can be produced by asymmetries in the explosions seem compatible with observations. So that seems we're not completely off track. Open questions, and I'm almost at the end of part one. Open questions, things like magnetic fields. The magnetic fields are becoming a very hot topic, actually. And in recent years, that's partly been my fault. We have even started to look more at them in the context of non-rotating core collapse supernovae, where you can still get amplification of magnetic fields by the small-scale dynamo, probably to a point where you get about to 40% of kinetic equipartition with the convective motions. And I think, though, speaking fairly, the question whether the magnetic fields really matter very broadly, so not just in the context of very rapid rotation, I think it's a borderline case, because what we are seeing is, well, maybe under certain conditions, they can be another factor that helps turn things around towards explosion. But more generically, with recent studies that my former PhD student, Bailey Sykes, has done, we are also getting to the realization that maybe, well, they are not the thing that will change our explosion energies by factors of 2 or 3, because actually after the explosions kick in normal non-rotating supernovae, the field amplification actually winds down and the magnetic fields again become less important. I'll skip the thing about black holes and just talk about magnetic fields in a more general context. I think there's been a lot of energy in terms of modeling magnetorotational explosions, which is perfectly fine. I think the thing there is we need to cope with the huge uncertainties that we have on the progenitor evolution. Is the initial rotation? What are the initial magnetic fields? So there's a completely unsolved area and stellar evolution that we simply have to rely on. That's not a great situation that needs to be remedied. And despite the fact that many of us are able to get MHD-driven explosions with various codes, if you look into the details, there are still differences, and the way to sort things out is to go more into the direction of code comparisons and ensemble modeling, which is actually a pain in the neck in 3D and 2D. It's awfully complicated, I can tell you. But that's also what we need some resources for, right? So winding up, in terms of the modeling effort, we are facing a huge challenge actually in supernova modeling, because if we really want to push supernova modeling to multi-messenger astronomy, you have you're facing a pipeline from the progenitors through explosion modeling to light curves and so on, and you will have a lot of efficiency losses in the pipeline, right? You can do, if any of these steps is difficult for your PhD student or master student to make, how often will you go through this pipeline? Not very often, right? So these challenges of putting things together, putting the, let's say, the core of the problem, at least we like to fancy that's the core, right? The modeling of the explosion engine together with the progenitor modeling and with the multi-messenger modeling is going to require us, I think, also to adjust organizationally. And that's also something that I would like people to discuss at this meeting, perhaps. Not just the science, but also how do we prepare for the challenges of multi-messenger astronomy organizationally and technically. Let's not forget that's also an interesting question because that is what enables the science. And with that, I think I conclude the first part of my lecture before moving on to the gravitational wave part later.
That's the nice thing about having dear friends who are experts. You ask them to do the impossible and they do it. We're going to have a coffee break. Before we break, I'd like to entertain a few quick questions from part one, and because obviously we'll do the same after part two. Any questions? Yeah, Chris?
So one of the issues that we have with these multi-D models is that the numerical viscosity is way higher than nature produces. How are we going to get around that in the near term? Because it alters how the convection grows and all this.
Yeah, I mean, the way I would phrase it, and there's like some work on that has actually been done, is, I mean, as long as you still trust that we have some kind of self-similar scaling behavior of the turbulent flow above certain critical Reynolds numbers, that's what you have to trust. Then you can still trust that, well, if you were to increase your resolution ever more and ever more, at some point, nothing much substantial would happen. Or at least you could extrapolate things like, yeah, what's your efficiency for converting neutrino heating into convective, turbulent convective energy? I think that's the only way. I mean, Thomas and Tobias Milson, for example, have done some very nice work on resolution studies and the implications of resolution for the core-collapse supernova heating to convection conversion problem. I think that still remains the only way. Where I'm really worried, though, is when we're talking about some MHD effects, because then you have to very smartly combine microscopic DNS-like studies that extrapolate from the correct regime of microscopic conduction coefficients and transport coefficients to the physical regime that we're actually facing. I think that's another important issue that, especially in the magnetic field sector, that we're going to face is extrapolate more or study more and extrapolate from idealized simulations and then try to bake that by appropriate means into the behavior of your simulations by tuning things like effective dissipation or, yeah, how that is to be done. I think I have to be fuzzy about that. But I think what we need to do is we need to find ways or think about ways to mimic the correct asymptotic behavior, perhaps by including appropriate modified equations in the way of subgrid models, et cetera, et cetera.
Microphone.
One question about black hole formation that you skipped through a little bit. Is there any consensus of the needed mass of the proton neutron star for black hole formation, or is something where you hope that gravitational wave observation, if it happens, will help you to constrain
I
that?
don't think we can have a I don't think the modelers can have a consensus on that, because it's ultimately a question that has to be passed back to the nuclear equation of state community as well. There are uncertainties in the nuclear equation of state, and we can't resolve that. And I can definitely tell you, we actually like to think that we have the equation of state now quite well under control in the regime where we're talking about normal neutron stars, but I can tell you, when you're pushing to the regime close to black hole formation, very massive neutron stars, they will affect your dynamics in the simulations. And there we are still, no matter how much we may believe neutron star radius measurements for normal mass neutron stars, if you're talking about 2 solar masses upwards, your supernova simulations will still depend on details of the nuclear physics that we haven't constrained.
And on that note, just one of the wonderful things about this symposium, the fact that everyone has come and taken the time out, is we have experts in each of these areas who will speak to these issues. So the idea was to bring the experts together to address all of these facets of the supernova problem on the theory side, and obviously the same for the detection side. So I think